All right, so part 2 of the 5-6 notes. So 5.6 part 2. It asks us to find the inverse of each function by identifying an appropriate restriction of its domain. Okay. So here we have f of x equals x squared plus 8x plus 16. As a friendly reminder, whenever I algebraically find an inverse, the first thing I'm going to do, thank you, is replace f of x with y. So instead of f of x equals x squared plus I'm going to write it as y equals x squared plus 8x plus 16. It looks like wish and not with. My bad, chat. Alright, step 2. I'm going to switch. I'm going to switch x and y. So everywhere I see an x, I'm going to make it a y. Everywhere I see a y, I'm going to make it an x. So instead of y equals all this, I get x equals y squared plus 8x plus 16. Oh, excuse me, that's a y. My bad. Good job, good job. Nice catch. Nice catch. All right, now step 3 says solve for y. And then, it's kind of gross. For this problem, how do I go from a trinomial into just something that has only one y? Right, if I'm solving for y, I have 2 terms with a y in it, and that stinks. So, let's try factoring. What's the only thing that's going to get me y squared? A y and a y. Factors of 16 that are closest together are 4 and 4. The second sign here is a plus, so we have to have the same signs here. And the middle sign, or the first sign here is a plus, so that both signs have to be plus. And when I check this, 4y plus 4y will get me 8y. So I can tell these are the factors. But what's another way of writing y plus 4 times y plus 4? Yeah, y plus 4 squared. So x now equals y plus 4 squared. Oh, nice. Now I have one y. And that guy we can solve for. So here we would square root. So we're going to square root both sides. And now I get plus or minus root x equals y plus 4. And then we subtract 4. So negative 4 plus or minus root x is equal to y. Now, what do we know? That original graph is quadratic and it's going to be a parabola. Will a parabola ever pass a horizontal line test? No. And in general, we want to cut off the left half of that. Right? We want to cut off the left half of that parabola. So I want to go back to this idea right here. X equals y plus 4 squared. What the original graph, that tells me the original graph is y equals x plus 4 quantity squared. Think about your transformations for a second. If I had a regular parabola on the parent function, it starts where the vertex at the origin, correct? What does that x plus 4 do to this graph? It shifts to the left 4 units, right? So now I have a parabola that looks like this. So what is the x value that's going to cut off the left half of that parabola? Negative 4. So what domain should I have for the original function? What's my domain have to be so that I have the inverse be a function? Negative 4 to infinity. Yes, good. So let's say that the domain here is going to run from negative 4 to infinity. And when I do that, I am now effectively cutting off the left side of that parabola. Okay? When I reflect it, I'll end up with a square root that opens up. That's a square root that's opening up. So do I want the positive or negative square root? I want the positive square root. So that means that the inverse function is the positive square root of x and then minus 4. And if we think back to 5.2 where we were, or 5.3, where we were shifting graphs of square root functions, that negative 4, is that an h or a k? That's a k value, meaning it's going to shift down 4 units. Well, when we reflected that graph, it looks like that radical function, that square root function, has been shifted down 4 units, right? So that tells me we're doing this correctly, right? So that would be our inverse function. All right, let's try this other one here. What would the transformation be for that function right there? Down 9 units. Yeah, exactly right. So that graph, instead of being a vertex at the origin, the vertex is going to be down here somewhere. So how could we restrict the domain to cut off the left half of that parabola? 0 to infinity, that's right. So we're going to say here our domain is bracket 0 to infinity, parenthesis there. Right, 0 is included. All right, now let's go find that inverse function. All right, step 1. Oh, sorry, I forgot my last step. No. Step 4 is replace, sorry about this, chat, replace y with f inverse of x. My bad. So over here, let's go back to our step 1. We have our function f of x equals x squared minus 9. Step 1 says replace f of x with y. This is just housekeeping. This really, it takes no mathematical skill whatsoever. And we're here. Step 2, this is where we handle the inverse. Right? The inverse in general just means switch. What am I going to switch around? I'm going to switch around the x's and the y's. That's exactly right. So instead of y equals, I now have x equals. Instead of x squared, I now have y squared minus 9. All right, what do I got to do to get y by itself? What's my first step going to be? Yeah, let's get that 9 over. Yeah, so add 9 to both sides, so we get x plus 9 equals y squared. And finally, last step here, square root. Do I need the plus and minus? No. I've handled that with our domain restriction. I only need the positive version. Because we cut off the left half of the parabola, right, at this moment we cut the left half of the parabola off. So when I take the square root here, I don't need the positive and the negative. This allows me just to take the positive square root. So y is now by itself, and we have the square root of x plus 9. Now that y is by itself, I can replace that final y value with our inverse notation. So we have f inverse of x equals the square root of x plus 9. I like visuals. I like to be able to see what I'm doing sometimes. So if I go back to this crappy graph that I just drew over here, if I take away the left-hand side, and I fold that half of the parabola, if I fold it over the line y equals x, that 0, negative 9 becomes negative 9, 0 here. And all of these points on that parabola now form that square root. So yes, that definitely checks out. That square root function would have been shifted to the left 9 units. Is it true that that h value inside that radical would tell us that that square root function shifts to the left 9 units? Yeah, that x plus 9 inside the radical means we're going to shift the parent function to the left 9 units, which is what we saw here with the graph. So it definitely checks out.
Mr. Stevens, what's that about the f?
F inverse. So that looks like it's an exponent of -1, right? Or I would say exponent is not true. It's a superscript, a -1, which makes it look like an exponent because exponents are superscripts, right? So that is our function inverse. That's the inverse notation. So I will write it like this. Inverse notation is the symbol that we use, and we read it f inverse of x. So instead of f of x, we normally say f of x. What we're really saying here is f inverse of x. Okie dokie. All right, so they're going to run through another example here for us. Thank you. Find an equation of the inverse function for f of x equals the square root of.
Yep. I do have a question.
Yeah, hit me.
Like, if you look at it, I mean, we could already see it's a exponent, right? So would we be able to just get the inverse based on the original one without having to do all of it? Because all you have to do is really just switch.
Switch your x and y values. Are you looking at the graph?
I'm looking at the one we just did. So like it's x squared minus 9.
Yeah.
And then we get the square root of x plus 9.
Yeah. So you're not necessarily wrong. However, I will caution you big time. You will have to know your order of operations well enough to be able to do reverse order of operations. So you have to do it backwards and in the opposite order, right? So if I were to spell this out, so just to hunt this down, if I drop a number in here, if I drop a number in for x, describe the order of operations. What would you do first?
Solve the square or whatever.
Yeah, so you would square it. You would square it first, and then after you did that, what would you do?
Subtract the 9.
Subtract the 9. Exactly right. So that would be the precise order of operations, right?
Yeah.
Now, you have to go in reverse order with inverse operations. So instead of going square and subtract, you would have to add 9 and then root. Does that make sense?
Yeah.
Because, again, opposite order, opposite operation. So you just take an x, add 9, and then take the square root of all that. And that's where we ended up. Does that make sense? Mm-hmm. Like, what happens if I just drop a number in? If I just drop a number in, follow your order of operations. Or you write that down, because it's not always going to be as simple as square it and subtract 9. It could be a bunch of different things. Mm-hmm. But also, what happens if you do that here?
Yeah.
You know what I'm saying? Like, if I follow the order of operations here and then try to go through in reverse order, that's not going to work because there's something far more simple happening right here. Does that make sense?
Yeah.
So after we manipulated it to look like y equals the square, x plus 4 squared, then we could go back and do the order of operations, right? We add 4 and then square it. So that means we would have to square root and then subtract 4. So square root and then subtract 4. If I did it from here, you're safe. If I tried to do it from here, you're in trouble. Mm-hmm. Does that make sense?
Yeah.
Okay. Did that answer your question?
Yeah.
Okay, good, sweet. All right, so taking a look at this guy. It asks us to find the equation of the inverse function for f of x equals the square root of x minus 2. So on this guy here, what they're really getting after, they switch from f of x to y, right? They follow that step. Then they switch their x and their y around. Sweet, they follow that step. Then they square both sides and then they add 2. So they're here. At this point, they can now say f inverse of x equals x squared plus 2. But they give us this error. It says don't apply the inverse notation too quickly. This notation is only used when the inverse of f is a function. Check to see the domain needs to be restricted for the relation to be a function. Would we... excuse me. So, we have to check to see the domain needs to be restricted for the relation to be a function. So, if you go back to the original function is a square root. The domain is 2 to infinity. The range is 0. So, I don't like the way they say it here. So, if I'm thinking about f of x, the domain we said was from 2 to infinity, and the range is from 0 to infinity. Now, for the inverse function, if we're switching x's and y's, we're switching our inputs and outputs, then for the inverse, what do you bet we have to switch our domains and ranges, right? So, what will the domain be for the inverse? 0 to infinity. 0 to infinity. Yeah, we don't have to reverse order with this. That's just with the order of operations and all that. We just take whatever the domain is and make it the range, and whatever the range is becomes the domain. And so here, what will the range become? 2 to infinity. Exactly right. Yeah. They said it, but I kind of like seeing it as this as well. And let's think about that for a second. What is the transformation for that parabola? Up 2 units. Yeah, so if I were to graph that, I go up 2 units and I draw my parabola, right? However, for the inverse function, the domain goes from 0 to infinity. So I cannot draw the left half of that graph. It starts at 0 and goes to infinity. That's what the domain told me I was allowed to have. Now, does the range fit? Does the smallest y value, is my smallest y value here, is my smallest y value at 2? Yeah, that absolutely checks out, right? Is that helpful?
So what happens if the range doesn't?
Go ahead.
Again?
What are you saying? If the range doesn't match the graph?
Yeah.
That would be dang near impossible. Yeah, that would be impossible. What I did is I just took the original, the way I kind of like thinking about this. If you take the original domain and range, here's your original domain and range, and you flip it around, then you go find the function, and then you take that function and you say, well, I can only graph x values that are bigger than 0, so I can only graph the right side of that parabola. And it will always work out that the range here will match the original domain when you do that. Always. I just wanted you to see with your eyes that it absolutely fits, and it also still holds true that your transformations will help you see it. Was that helpful?
Yeah.
Okay, good. All right, roll it over, Smokey. We literally just did that.
Oh, yeah.
Yeah, so, sorry, not going to make you do that problem. All right, let's go here. Find an equation for the inverse function of f of x equals negative cube root 4x. So, let's start here. What is our original domain? Look at this graph. What's the domain got to be?
Negative.
Yeah, that's it. Yeah, that's it. And our range?
Negative.
Yeah, good. So do I need to worry about any restrictions then? No, I don't have to worry about any domain restrictions. All I most literally have to do now, is the algebra, right? Switch that from f of x to y. So I have y equals negative cube root of 4x. Switch around my x's and my y's. So x equals negative cube root of 4y. What's your first step going to be here, Dan? Yes, dude. Let's go. Divide by -1. Divide by -1. X divided by a -1 is -x. And that's equal to the positive cube root of 4x. Cade, what are you going to do next? Oh, it's 4y. It's a y, it's a y, it's a y. David? Yeah! I'm going to make both sides the power of the index. Our index is a 3, so we're going to cube both sides. Good job, homie. So that means that -x cubed is equal to 4y. Last step.
Divide by 4.
That's it. Divide both sides by 4. So now I have y is all by itself, and we have a -x cubed all over 4. Okie dokie. Any worries about our domains and our ranges? Nope. So now I can replace that y with f inverse of x is -x cubed all over 4. It's not too terribly difficult. Hopefully it's not too terribly difficult. Oh, this is so exciting. So exciting. All right, roll it over, Smokey. All right. All right, so we have 2 minus the cube root of x plus 1. Yeah, man. I'm going to rewrite that as f of x equals negative cube root x plus 1 and then plus 2. So there are 3 transformations. What are the 3 transformations for that cube root function? Shift up 2 units, good. Left 1 unit, and reflect. Yeah, so we have to reflect. We're going to go left 1 and up 2. So if I think about this graph, I'm going to go left 1, up 2, here. Right, and a normal cube root goes bottom left, Snake River, top right, and it's pretty flat. That's our normal one. Now if I reflect that, it's going to look like this guy here. So that's the function. Any restrictions on our domain or range? No. So I'm just going to make a note, no restrictions. I don't even need to write out my domain and range because it's all real numbers. It's all real numbers. So, did we verify that the inverse will be a function? Not fully. Does this function pass the vertical line test? Yes. Does this function pass the horizontal line test? Yes. So there are no restrictions. It passes both the vertical and horizontal line test, so we verified that the inverse will indeed be a function. So now we got to go find the inverse function. We have y equals. Would it be easier to see it the h plus k or the original? What do you think? H plus k?
Yeah.
All right, so we have negative cube root x plus 1 plus 2. What's our next step here, Cade Winkleman? Easy. Before I start solving. What's the big word when it comes to inverse, big dog? Switch. Yeah. What do we have to switch? The switch around the x and the y. Good. So the x goes here. The negative cube root of y plus 1, all of that plus 2. Yeah. Now we can start solving. Now what's going to be your next step, Cade? Perfect. So x minus 2 equals negative cube root y plus 1. What's your next step? Cade?
Divide by -1.
Beautiful. Divide by -1. Divide by -1. Alright, so we get negative x plus 2 equals the cube root y plus 1. Next step, cube it. Got to get rid of that radical. Good job, dude. Oh, biscuits. Okay, I'm going to make some room for myself. We have negative x plus 2 cubed equals y plus 1. Sweet, last step.
Oh, subtract the 1.
Perfect. So all of that, I have y now is by itself, so I like to move it to the left hand side. So y equals the quantity negative x plus 2 cubed, all of that minus 1. And since we've already verified that it will be a function, I can now say f inverse of x equals, and I need to be very clear, negative 1, there we go, negative x plus 2, quantity cubed, all minus 1. Da, 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 da. Questions about it? So far, so good?
Yeah.
All right. Let's do another one here. One more real quick, and then we're going to get to some good stuff. All right. What is the inverse of this guy? What is the shape of 2x plus 5? It's a line. It's linear. Note all linear functions I want to be clear, functions can be inversed. That's a dumb way of writing it. It's not mathematical at all. We can always find the inverse of a linear function. There are no restrictions. Here, we're going to say that. There are no restrictions. Ooh, what if I say it this way? All linear functions pass both the vertical line test and the horizontal line test. There we go. Hey, that's a great way. There we go. I feel gooder about that. Can I speed run this? Thank you. Switch that to y. So y equals 2x plus 5. Switch! It's an inverse. X equals 2y plus 5. Solve. Subtract 5. X minus 5 equals 2y. Divide. When I divide this, though, I'm going to divide all three terms by 2. I don't want to do one big all over 2 because that does not tell the full story of what's happening over here. So I'm left with y equals 1/2 x minus 5 halves. No MFs, please. Mixed fractions, I don't like them. Now that I'm here, I can rewrite it as f inverse of x equals 1/2 x minus 5 halves. Now, they left a little clue down here. And this is a function composition. Alright, so what this says, if I plug a function and its inverse into each other, the result should just be x. It should just be x. So what we're going to do is we're going to do f composed with f inverse at x. I'm going to do that first. So that's to say f of f inverse of x. The f function is 2x plus 5. So I have 2x plus 5. What's going in for x is the inverse function. Our inverse function is 1/2 x minus 5 halves. So 1/2 x minus 5 halves. Now when I go simplify this on the right hand side, I'm going to distribute the 2. 2 times 1/2 is 1. What's 2 times negative 5 halves? Negative 5. So x minus 5 plus 5. Yeah, hurry back. And negative 5 plus 5 is gone. And what are we left with? Just an x. I can also say f inverse composed with f at x. That is to say f inverse of f of x. So this time I'm going to start with the 1/2 x minus 5 halves. So 1/2 x minus 5 halves. And I'm going to put the original function in. The original function is 2x plus 5, so 2x plus 5. Now when I distribute my 1/2, 1/2 times 2 is just 1x. 1/2 times 5 is a positive 5 halves. And then we're going to subtract 5 halves. Oh, nice. 5 halves minus 5 halves is just x. So this down here will hold true. That is an important one. Alright, roll it over, Smokey. Are these inverses of each other? Ooh, okay, so f of x and g of x. So let's try f composed with g. So f of g of x. Our f function is x squared plus 5. So x squared plus 5. What's going on here is the g function. We have the square root of x minus 5. And the square root of x minus 5 squared, that's going to give us x minus 10 root x plus 25 plus 5. And to simplify one more step, we get x minus 10 root x plus 30. Is that just x? No, that's not just an x. So sadly, here we can say f and g are not inverses. F and g are only inverses if f composed with g is equal to x, or also g composed with f. It has to go both ways. I have to be able to take the inverse function into the original to get x, then I have to take the original function into the inverse to get x. Okie dokie. Alright. That is it. We did it. Way to go. Ta-da. The rest are practice problems. As always, if you have questions, please ask.